Hello guys, welcome to Motion with Constant Acceleration. I have a special video about acceleration. You can see the link of this video in the caption. And as another special video about the velocity time graph, you can see also the link of this video in the caption. But today, in part 1, I will start introducing graphs of constant acceleration motion, which is the very basic part. And then in part 2, I will continue with the equations, okay? Look at this x-axis. Suppose that a car starts from initial velocity of 2 meters per second to the right, and then after 1 second, the speedometer indicates 6 meters per second. Then I will read the speedometer after another 1 second to be 10. And at t equals 3, another 1 second, the velocity is 14. As you see, in each second, the velocity will increase for 4 meters per second. So 4 meters per second in each second is the gain in velocity, which is called acceleration. So acceleration is 4 meters per second squared. And it is very important, it's constant. Increase in velocity will not change. This is what we call constant acceleration motion. What about the velocity time graph? Velocity time graph can be plotted point by point here. It's very easy. At t equals 0, the velocity is 4. Initial velocity, the vertical intercept. And then at t equals 1, the velocity is 6. T equals 2, the velocity is 10. And t equals 3, the velocity is 14. If I connect those data points, I will get a line. This line has a special constant slope, which must be 4. Why? Because acceleration is 4. And the slope of VT graph is acceleration. So for finding the acceleration time graph, for drawing the acceleration time graph, I just establish a triangle here and then rise over 1, which is 12 over 3, and then I will get 4. Constant. Look, the acceleration time graph is a horizontal line. Okay, then xt graph. Xt graph will be a quadratic function. In part 2, I will explain it. But for the time being, please accept that the xt graph will be a quadratic function, so it's a parabola. The parabola is drawn very easily. It starts from 0 because x naught, the initial position, is 0 in this case, and so it will be a parabola like that. And after 3 seconds, the displacement is easily found by calculating the area under the VT graph. I explained it in the related video, you know that. Okay, so let's find the area of this trapezoid. The area will be delta x. This is the small base, which is 2, plus the larger base, which is 14, divided by 2 times the height. The height of this trapezoid is 3. So it will be 16 over 2 times 3, which is 24. So the total displacement is 24 after 3 seconds. This is a parabola. This is not a line because xt, I told you, is a quadratic function. I will explain it in part 2. Okay, this is everything you must know. Let's continue with more practice on these type of graphs and then problem solution. To summarize, velocity time graph is always a line starting from initial velocity, which is vertical intercept. It can be positive, 0, or negative. The slope is acceleration, and the area under the graph is displacement. Suppose that the initial velocity is positive, so the VT graph starts from a point above the t-axis. The initial velocity or the vertical intercept is positive. If the acceleration at the same time is positive, the line will be ascending because the slope is positive. Sometimes there is no acceleration, so it's uniform motion. There is no slope for velocity time graph. And the last may be positive velocity, initial velocity with negative slope, which is negative acceleration. The other will be the object which starts from rest. So there is no vertical intercept. If the acceleration is positive, it's ascending, 0, there is no motion, of course, and then the negative acceleration with descending line. The last is negative initial velocity starting from a point below the t-axis. If the acceleration is positive, so it's ascending line. If the acceleration is zero, uniform motion. And the last will be the negative velocity, initial velocity and negative acceleration, a descending line. Xt graph is always a parabola. It starts from initial position, it could be positive, negative, or even zero. And the initial velocity is initial slope of that. The initial slope is the slope of xt graph at t equals 0. It can be positive, 0, or negative. I will show you. Concavity is acceleration. Concavity means how the graph is concave. Sometimes the graph is concave up like this. So we can say acceleration is positive. Exactly similar to this case. Sometimes the acceleration is negative and the graph is concave down. For understanding the concept of concavity, also I have a video. The link of this video also is in the caption. You can watch that. Okay, let's consider different cases. Look at these three xt graphs. As you see, the first, the second, and the third are all concave down graphs because the concavity is negative in the three. So acceleration is negative in the three cases. But the velocity, the initial velocity is positive because at the beginning you see the velocity is positive. I see the positive slope at the beginning, at the start of the graph, okay? The last will be related to the initial position. Here, the first one starts from above the t-axis, so initial position is positive. The second one has no initial position, 0, and the last starts from the point below the t-axis, so the initial position is negative. Look at these three. They are all concave up, concave up, concave up. So acceleration is positive. The initial velocity at the beginning, this graph is descending, so initial velocity is negative, initial velocity is negative, initial velocity is negative in the three cases. The last will be related to initial position. Initial position here, as the graph starts from a point above the t-axis, is positive. In this case, initial position 0, and the last initial position negative, because the graph starts from a point below the t-axis. Look at these three. They are all parts of a parabola. But this parabola is concave up, concave up, concave up. Again, acceleration positive. But at the beginning, as you see, there is no slope. So initial velocity is 0. Initial velocity is 0. Initial velocity is 0 because the graph starts from minimum, extremum point. And the last is considering the initial position. Initial position in the first case is 0. The second case positive. And the last case, initial position is negative because the object starts from a point below the t-axis. Okay, look at these three. They are not lines, they are parts of parabola. Okay, they are all concave down, concave down, concave down. So I can say acceleration is negative in the three cases. The initial velocity indicates a negative value, you see, because all the graphs at the beginning are descending ones, so initial velocity negative. And about the initial position is very easy. It starts from a positive initial position, 0 initial position, and then negative 1. That's all. You can see them. It's very easy. Look at the next three. Again, I emphasize they are not lines. They are parts of parabola. They are all concave up, concave up, concave up. And so, because the graph is like that. Why we don't see the tail in the left side? Because there is no negative t in physics. This is why you see just a part of that. Anyway, the acceleration is positive. Okay, and then I will consider the initial velocity. At the beginning, it's ascending. At the beginning, ascending, ascending. So they have positive initial velocity. And then initial position in the first case, positive. The second, 0. And the last, the initial position is negative. Look at the last three. Concave down, concave down, concave down. So acceleration negative. At the beginning, They start from a maximum point, so there is no slope at the beginning. So the initial velocity is 0 in the three cases. About the initial position, it's very easy. It starts from 0, initial position 0, initial position positive, it starts from a point above the t-axis, and the last negative initial position. That's all. Now let's have some problem solution. An object has the VT graph below. Look at this, the VT graph seems to be a line, so acceleration is constant. Does it have initial velocity? Question number 1. Yes, of course it does, because it starts from non-zero velocity at the beginning. Yes, the initial velocity, of course, is a negative value, but yes, it does. It has a negative initial velocity. Question number 2. Consider the direction of motion. Direction of motion means the sign of velocity, if the velocity is positive or if the velocity is negative. If the velocity is positive, the object is moving to the positive direction of x. If the velocity is negative, the object is moving to the negative direction of x. From 0 to t1 here, the velocity is negative, so the object is moving to the left. Let's say this is the x-axis, and then the left is negative direction, the right is positive, okay? So here, from 0 to t1, the object is going to the left, negative direction of x. And here the velocity is positive from t1 to t2, so the object is moving to the positive direction of x. Let's say it's to the right. Question 3. Is it speeding up all along the motion? How can we know if the object is speeding up or slowing down in VT graph? It's very easy. When the VT graph is approaching the t-axis, it is a slowing down. So at the beginning, it's a slowing down. The reason is evident, because here the velocity is 0, okay? So from 0 to t1, the absolute value of the velocity, magnitude of the velocity is decreasing. The speed is decreasing. And then after t1, it is a speeding up. The reason, again, is evident because the speed is increasing. So when the VT graph is approaching the t-axis, it's a slowing down. When it is escaping from t-axis, it's a speeding up. Question 4. Is it a uniformly accelerated motion? Yes. Uniformly accelerated motion is another name for constant acceleration. Because the velocity time graph is a line, yes, acceleration is constant. So in other words, we can say it's uniformly accelerated. Is it true in this graph to say average and instantaneous accelerations of the object are equal? Yes, it is. Because the acceleration is constant. Constant because the velocity time graph is a line. So instantaneous and average acceleration must be equal. Yeah. Another question. Part A. Sketch the acceleration time graph for VT graph below. Look at this. The VT graph at the beginning has no slope, I think in 5 seconds. And then it has a positive slope, so positive acceleration. And the last will be a negative acceleration and motion. Okay, so let's draw it. At the beginning, for the first 5 seconds, there is no slope. The second part, positive slope. To find a slope, you can establish a triangle. This triangle has a rise and a run here. The rise seems to be 32 minus 16, and the run will be from 5 to maybe 9, so it's 9 minus 5. So it seems the acceleration to be 16 over 4. So acceleration is 4 in the time interval of 5 to 9. Then the last, again, a negative slope. Again, I establish a triangle here, rise over run. Rise is 32 and the run is from 9 to 13. So it will be, acceleration will be negative 32 over 13 minus 9. So it's gonna be negative 32 over 4, so it's negative 8. negative because the slope is negative. It's very important. But part B is very easy. Part B is about the distance traveled. The distance traveled in uniform velocity motion. Uniform velocity is exactly when the graph has no slope, so acceleration is zero. When the acceleration is zero, exactly at the beginning to the t equals 5, the first 5 seconds. So the part B is related to the distance traveled in the uniform motion. So I'm gonna find just the area under the graph, the VT graph between 0 to 5. It's a rectangle, and the vertical is 16 and the horizontal is 5. So 16 times 5 is 80 meters. The displacement or the distance traveled in the first 5 seconds, uniform velocity part. An object moving with constant acceleration has an initial velocity of 4 meters per second. After 6 seconds, the velocity is 12, increased. Determine the acceleration and displacement of the object during the first 6 seconds. VT graph is the solution for all these types of problems. So the graphical view will start from the VT graph, starting from 4, the initial velocity 4, and then raised to the 12. As you see, in 6 seconds, the velocity increased. So I see the positive acceleration. How to find the acceleration? Just establish a triangle. Rise over run. Rise is 12 minus 4 and the run is 6. So the acceleration will be 12 minus 4 over 6. So the answer will be 4 over 3. So the acceleration is 4 over 3 meters per second squared. How to find the displacement? Displacement is the area under the graph. From where to where? From 0 to 6. This is a trapezoid. Small base is 4 and the large base seems to be 12. So delta x, the displacement, will be large base plus small base times the height. Height is 6 here, and then divided by 2. So delta x will be 48 meters. Of course, in this case, from 0 to 6, as the velocity has always a positive value, there is no change in direction of motion. So also I can claim that rather than the 48 to be the displacement, also it's the distance traveled. But if the velocity changes the direction, you must be very careful about that because displacement and distance may be different. For instance, if the VT graph is something like that, here I have a turning point. So the distance and displacement from 0, for instance, to 6, in this case, cannot be equal, okay? A cyclist slows down uniformly from a speed of 7.5 meters per second to a speed of 2.5 meters per second in 5 seconds. Calculate the acceleration, the distance traveled in 5 seconds. Again, I start from VT graph. VT graph is solution for all these types of problems in constant acceleration motion. I love it. The next video, of course, I will explain everything for the related equations, but mostly I prefer the graphical approach. Okay, the initial velocity is 7.5, then it drops to 2.5 in 5 seconds. You see the acceleration is negative. How to find it? I just establish a triangle and then rise over run. Rise is 5, run is also 5. So 5 over 5 is 1, but negative 1. Pay attention, the acceleration is negative. The distance traveled. Distance traveled is the area under the graph from 0 to 5. It's again a trapezoid. Large base is going to be 7.5. A small base is 2.5. 2.5. So delta x will be 7.5 plus 2.5. Large base plus small base times the height. Height is 5 divided by 2. So it seems to be 10 over 2 times 5, so it's 25. 25 meters of displacement in the first 5 seconds. A cyclist moving with constant acceleration has the speed of 4 meters per second at x equals 12. So let's say this is the x-axis. At x equals 12, the object has a speed of 4 meters per second to the right. and then the speed of 5 meters per second, 5 meters per second at x equals 21. Okay? Part A, the time interval and the acceleration. Okay, here I see the displacement of 9 meters. Okay, during the 9 meters, it has a raising the speed from 4 to 5. Let's draw the VT graph again. The VT graph must be something like this with constant acceleration as mentioned here. The velocity here could be 4. I don't know the time. And the velocity at the later time at x equals 25, I don't know when, will be 5. Okay, so the velocity raised from 4 to 5 just in 9 meters. 9 meters means the area under the graph is 9. So here something I should know is the delta t. You see there is a trapezoid. The height of the trapezoid is delta t. The small base is 4 and the large base is 5. So as I know the small base, the large base, and the area under the graph, I can easily find the delta t. How? You know that 9 is the area, so it could be the small base plus the large base times the height, the delta t, over 2. That's all. So here delta t must be 2 seconds. Okay? How to find the acceleration is very easy. Acceleration is the slope of this graph. As I know the delta t here, which is 2 seconds now, so rise over run. Rise is 1, run is 2, 1 over 2 is a half. So acceleration here must be just a half of meters per second squared. That's all. I'm sure that you enjoyed, and it was the first time you see that in constant acceleration motion we can solve the problems just based on graphical approach. Next video I will have more explanation about the graphs, and I will continue with introducing different related equations. Okay, just please review the lessons and then go to the next part. Thank you. Take care. See you.